Okay, so let's go ahead and get into remote sensing, collecting data from a distance. So, remote sensing is the geospatial science related to obtaining data from a distance using devices that detect emitted or reflected electromagnetic energy. Remote sensing applications produce raw geospatial data, usually as images. Let's first define the idea of remotely sensed data. Broadly speaking, within the context of GIS, there are two common types of remotely sensed data: aerial imagery and satellite imagery. Aerial and satellite imagery are both remotely sensed data because it records reflected energy from a distance. This remotely sensed information is useful for many reasons, such as a large area coverage in a single capture, its ability to look outside the visible spectrum of the electromagnetic spectrum, its geometric accuracy once it's rectified to Earth-based coordinate systems, and the fact that it is a permanent record of a single snapshot in time. So, electromagnetic energy transferred by radiation is known as electromagnetic radiation, or EMR. EMR is the only energy that can travel through a vacuum, such as interstellar space. Light, electromagnetic waves, and radiation all refer to the same physical phenomenon: electromagnetic energy. All objects warmer than absolute zero emit electromagnetic radiation, or EMR. This means that the sun, the earth, and even your computer monitor are reflecting and emitting a wide range of electromagnetic waves. Objects also reflect and absorb EMR emitted by other objects. The sun is a major source of electromagnetic radiation, emitting energy across several regions of the spectrum. All of this is key to remote sensing because Earth's surfaces reflect the sun's electromagnetic energy in unique ways. The entire range of electromagnetic waves is known as the electromagnetic spectrum. There are 5 major regions of the remote sensing electromagnetic spectrum, and they range from gamma rays to radio waves. All electromagnetic radiation has fundamental properties and behaves in predictable ways according to the basics of wave theory. Electromagnetic waves are formed by the vibrations of electric and magnetic fields. Electromagnetic radiation consists of an electrical field which varies in magnitude in a direction perpendicular to the direction in which the radiation is traveling, and a magnetic field oriented at right angles to the electrical field. Both of these fields travel at the speed of light. Electromagnetic waves differ from mechanical waves in that they do not require a medium to propagate. This means that electromagnetic waves can travel not only through air and solid materials, but also through the vacuum of space. Electromagnetic radiation can be described in terms of its frequency, wavelength, or energy. The entire range of electromagnetic waves is known as the electromagnetic spectrum. This includes electromagnetic energy ranging from gamma rays to radio waves. The electromagnetic spectrum is broadly classified into different named categories based on the wavelength and characteristics of the energy. The only region in the entire electromagnetic spectrum that our eyes are sensitive to is the visible region. Gamma rays have the shortest wavelengths and the most energy of any region of the electromagnetic spectrum. Gamma rays are produced by the hottest objects in the universe, including neutron stars, pulsars, and supernova explosions. Gamma rays can also be created by nuclear explosions. The majority of gamma rays generated in space are blocked by the Earth's atmosphere. This is a good thing, as gamma rays are biologically hazardous. There are also X-rays. X-rays range in wavelength from 0.01 to 10 nanometers and are primarily generated from one superheated gas from exploding stars and quasars. X-rays are able to pass through many different types of materials. X-rays are commonly used for medical imaging and for inspecting cargo and luggage. Similar to gamma rays, the Earth's atmosphere blocks X-ray radiation. So both gamma rays and X-rays are not included in the remote sensing 5 major regions of the electromagnetic spectrum. So the 5 major regions of the remote sensing electromagnetic spectrum include UV, visible, infrared, microwave, and radio waves. And we'll go over all of those in the next few slides. So first we have ultraviolet. Ultraviolet light has wavelengths of 10 to 310 nanometers. The sun is a source of ultraviolet energy. The UV portion of the spectrum is subdivided into UVA, UVB, and UVC. UVC rays are the most harmful and are almost completely absorbed by our atmosphere. UVB rays are the harmful rays that cause sunburn. Although UV waves are invisible to the human eye, some insects, such as bumblebees, can see them. So visible light covers the range of wavelengths from 400 to 700 nanometers. This is the only region in the spectrum that the human eyes are sensitive to. The sun emits the most radiation in the visible portion of the spectrum. Each individual wavelength within the spectrum of visible light wavelengths is representative of a particular color. The light at the lower end of the visible spectrum, having a longer wavelength, about 740 nanometers, is seen as red. Light in the middle of the spectrum is seen as green. And light at the upper end of the spectrum with a wavelength of about 380 nanometers is seen as violet. When all the wavelengths of the visible light spectrum strike your eye at the same time, white is perceived. The visible portion of the spectrum is used extensively in remote sensing and is the energy that is recorded using photography. So here's another slide for a visible spectrum. The color of an object is defined by the color of light it reflects. We see a red apple because it reflects red light. Intermediate colors are formed when an object reflects 2 or more of the additive primaries, red, green, blue, which combine to form yellow, red and green, magenta, red and blue, and cayenne, blue and green. So the infrared portion of the spectrum ranges from approximately 720 nanometers to 1,000,000 nanometers in wavelength. It is divided up into 3 main regions. We have the near infrared, shortwave infrared, and the far or thorough infrared. Infrared radiation is used extensively in remote sensing. Objects reflect, transmit, and absorb the sun's near infrared and shortwave radiation in unique ways, and this can be used to observe the health of vegetation, soil composition, and moisture content. The region from 8 to 15 micrometers is referred to as thermal infrared, since these wavelengths are best for studying the long wave thermal energy radiating from the Earth. So here we can see the difference in 2 images. The one on the left is visible and the one on the right is infrared. So this comparison of the Carina Nebula and visible light, like I said, on the left, and infrared on the right, and both of these images were acquired by the Hubble telescope. And so infrared penetrates much of the obscuring dust and gas and unveils a more unfamiliar view of the pillars. And so here, newborn stars hidden in the visible light view can be seen forming within pillars themselves. So we can see this here in the visible, and then we get much more detailed of those stars with the infrared. Infrared energy falls just outside of the red visible light region of the electromagnetic spectrum. This image is an example of near infrared and is a band within the infrared region on the electromagnetic spectrum. It ranges from 700 to 1300 nanometers. Applications of near infrared include vegetation mapping. Chlorophyll has a high reflective value in the near infrared portion of the electromagnetic spectrum and can help determine the health of vegetation. So microwaves are essentially high-frequency radio waves and have wavelengths that range from 1 millimeter to 1 meter. Different wavelengths or bands of microwaves are used for different applications. Mid-wavelength microwaves can penetrate haze, light rain, and snow, clouds, and smoke are beneficial for satellite communication and studying the Earth from space. Radar technology sends pulses of microwave energy and senses the energy reflected back. Radio waves have the longest wavelengths in the electromagnetic spectrum, with wavelengths ranging from approximately 1 millimeter to several hundred meters. Radio waves are used to transmit a variety of data. Wireless networking, television, and amateur radio all use radio waves. The use of radio frequencies are usually regulated by governments.